Okay, this next series we're going to discuss is factor number one that directly affects your collisions. Because the rate of a chemical reaction is going to be controlled by two concepts on the collisions. How many times they collide? Because by probability, the more times they collide, the greater the probability of breaking bonds, and therefore the faster getting to what they call the intermediate. So the frequency of collisions plays a role. And then now when they collide, obviously you want them to collide effectively. So when it comes to those collisions, it's not just how many times they're going to smack up into each other, but also how effectively are they going to align in order to break their bonds and therefore create what we call that activated complex, which is that highly unstable thing called this intermediate, this thing that you create before you get to your products. So what's controlling the speed of the reaction of these collisions? And one of the things we said that was the first thing that affects collisions is what we refer to as the nature of your reactants. Now, the nature of reactants, the first critical thing, is what phase are they in? Phase plays a major role because in order to collide, your mobility will play a role. So the gaseous phase, for example, chemicals in a gaseous phase will always react faster than chemicals in a solid phase, which is all the way at the end of the spectrum. Now, anything that you can do to increase mobility, let's say, of your solids, you would increase the solid reactants, you would increase the rate of the reaction. And a great example of that would be like Alka-Seltzer. Alka-Seltzer tablets, an antacid. It's not really a pure antacid because what you have in Alka-Seltzer, you actually have all the ingredients that you need for a chemical reaction in the tablet itself. You have sodium, hydrogen carbonate is the main ingredient, but you also have acids, weak acids. And we know in chemical reactions that hydrogen carbonate ions react with acids. They'll break down and produce CO2 and water. So technically, the ingredients you need are already in the tablet. So your tablet's in the solid phase and it's sealed in a very tight container so it cannot get contaminated. And it has an expiration date on it. So in theory, the reactants you need for that reaction to occur are already there. The question is, it's reacting really slowly. How do we know that? Because they're in solid phase. And these reactants are really unable to collide with each other that effectively because there's also what they call binders incorporated into the tablet, which interfere with the reactants combining, but also its purpose is to keep the reactants together in the tablet. So once you take those tablets and you dissolve them in water and create these ions, now you're going to increase the rate of your reaction. So the second state, which would be the most effective in collisions, are ions in solution. You have ions in solution. They're going to increase your rate of reaction. Two reasons. One, the charges themselves will force the collisions to occur effectively, and now they're much more mobile. So that's an example of, by changing the state of your reactants, you can immediately increase the rate of your reaction. Another key thing would be the Alka-Seltzer tablets themselves. If you were to take an Alka-Seltzer tablet, one of them, and crush them, and place them in a specific amount of water, and then take another one and just leave it as a whole tablet, you'll note that the one that's crushed will increase its rate because what you're doing is you're creating surface area for collisions between the chemicals and the water. So by crushing the tablet, you'll speed the chemical reaction. Another key example of the nature of the reactants related to phase is the burning of methanol. If you recall when we did the whoosh bottle demonstration where we had a water jug that contained methanol vapor, the reaction was quite violent. And the reason for that is because what's reacting is methanol in the vapor phase, in the gaseous phase. Versus if you took some methanol and you put it into a dish and you lit the dish, what you would notice, you'd see a flame. But the flame would be on the surface of the liquid. Because what reacts faster is the vapor of the methanol than the liquid. So the methanol will burn before the liquid will. And that's why sometimes we use the example of what's more dangerous, a half a tank of gas or a full tank of gas in an initial collision in an accident. Well, a half a tank of gas would be quite explosive on contact because it's mostly vapor compared to the liquid, and that will react a lot faster and generate a lot of energy faster. Remember here we're talking about speed, not amount of energy, but how fast you react to generate that energy. So these studies that we're talking about have to do with speed. So when you're comparing solids to gases, gases are the winners when it comes to reactants. So gas is the winner. Then ions in solution would obviously be more effective than if you had pure liquids. Yes, the liquids will be mobile, but if you have ions in solution, they're going to have more effective collisions because they have charges. And then last but not least would be your solids, which would be the worst state to be in. The other key thing about the nature of the reactants, what kind of reactants are we working with? Ionic compounds, for example, will always react, ionic reactants will always react faster than molecular reactants because they have ion charges. The Coulombic forces, and that's the Coulombic attractions, will increase the rate of the reaction because they make the collisions more effective because they're driven by the charges. Polar molecules, for example, will react better than nonpolar molecules because the charges will help initiate the effective collision between the reactants. And the worst would be your nonpolar molecules. There you would have the geometry of the molecule will play a role. How effectively can they align in order to collide the right way? Now, where do metals fit? Well, metals will fall somewhere between ionic and polar molecules. But the speed of a metal reacting is going to be directly related to the radius of the atom, which in turn is related to the radius of the ion in the metallic bonding. Again, here we're talking about speed. And now comes again the question of the difference between lithium in group 1 versus cesium or francium. Now, I'm not going to waste time with francium because francium is radioactive. But the fact is, we all know, based on our studies, our thermochemistry studies, that lithium reacting with water will generate more heat overall, more energy overall, because of the stability of the ion dipole attractions that you generate at the end of the reaction. But if you're talking speed, cesium will react faster than lithium, a lot faster, because the radius of a cesium atom or ion is much larger than the lithium. So the ability to lose that electron in that reaction goes to cesium as the winner. So cesium will generate the reaction a lot faster than, let's say, a lithium ion. But it won't generate as much energy overall, but it will generate the energy a lot faster. So the nature of the reactant plays a major role in kinetics.